Let's analyze and solve the valid anagram coding problem. We are given two non-empty strings s and t, and we have to return true if t is an anagram of s, otherwise we have to return false. So if we are given a string s, for the string t to be an anagram of s, the t has to be a permutation of s. If s is equal abc, the valid anagram in the meaning of this problem would be a string like, for example, t equals bca, because bca is a permutation of s, and what that means is that they both have the same length, they both have the same letters, and each letter in both strings appear the same number of times. The string t that would not be an anagram would be, for example, bbca. This is because they have different lengths and the letter B appears twice in string T and once in string S. Another example of a string that is not an anagram of S would be, for example, BBC. This is because the letter A is missing in string T, so even if the length of both strings are the same, they are not an anagrams. And I hope this explains the problem we are trying to solve. So from the coding perspective, we have to write a function. We can call it isAnagram. This function will receive two strings, s and t, and it will return a Boolean value, true or false, depending whether t is an anagram of s. We are also given a constraint, which boils down to the fact that the strings are not empty, so the length is greater or equal to 1. And we are also given additional constraint that the string only contains lowercase English letters. And there is an additional question for this problem, which asks us how would we adapt the algorithm if the string contained Unicode characters. So not only ASCII character, but the case where the characters are Unicode characters. And that's the problem we have to solve. To solve this problem, let's start from a simple brute force approach. And the first thing we will do is to compare the lengths of s and t. If they are different, we can return false because they cannot be anagrams of each other. If the lengths are the same, then what we will do next, we will sort both s and t, and after sorting we will compare whether the sorted s equals the sorted t. If they are equal, that means we are dealing with anagrams. If they are not equal, that means they are not anagrams of each other. And in the example 1, we have two words. If we sort them, for example, we sort s and we get s1 equal double E, D, triple S, TR. And if we sort t, we will get t1 equals double E, D, triple S, TR. And we will compare those two strings, S1 equals T1. And if they are equal, we will return true. If they are not, we will return false. If we do the same for strings in example 2, after sorting, we will end up with two different strings. It is because it's easy to notice that, for example, string S has a letter I that is not present in string T. So we will end up with two different sorted strings. And since they are not equal, we would return false. From the point of view of complexity, the time complexity of this algorithm is O of n log n. And the space complexity depends whether we are allowed to change the input data, in which case we can sort them in place and the space complexity would be O of 1. And if we are not allowed to change the input data, then we have to make copies, in which case the space complexity would be O of n. And when writing those formulas, we don't have to worry that the strings have different lengths, because this is the first check we did in our algorithm. We checked whether the strings are equal. So at the time when we reach the sorting and comparison, we know that strings are of the same length, and we can write the formulas using n as a size of the string. And that's pretty much all about the brute force algorithm. The brute force solution works, but we can improve time complexity switching to a different algorithm, and that algorithm will utilize a frequency counting. The idea is that for each of those two strings, we first check if they have the same length. This is the same as in the brute force algorithm. If they are different, then we immediately return. But if they have the same length, then we will create a frequency map for each of those two strings. So the way we can do it is to start from string S and count how many times each letter appears in that string, and then do the same for the string T. And once we have those two frequency characteristics done, we can compare them, and the comparison will be that they have to have the same letters, so the same keys, and the same values. So the way to implement this would be to use a map, and the map will have a character as a key, an int as a value, and the value will be a counter of how many times a given character appears in the string. And to populate this map, we would start from the first character in string S, and if the character is not in the map, as in our case, we would add this one to map with the value 1 and move to the next one. So T1, R1, E1, and we are positioned over S. S is already in the map, so instead of adding, we would increment the value from 1 to 2. Move to another letter, which is again S. So increment the value from 2 to 3. Next is E. We increment from 1 to 2. And we process D. It's a new letter, so we set D equal 1. And then we can create a similar map for string T. And once we have that map, we can go through each map and compare if they have the same keys, same letters. And if they do, then we can compare if for each letter the values in both maps are the same. And if they are the same for each and every letter in the map, then means the two strings are anagrams. And we can optimize this slightly. We don't need a second map. We can just go through the string T and decrement the counter instead of incrementing it. So the way it would work, we would start from the first letter D and decrement from 1 to 0, E from 2 to 1, S from 3 to 2, S from 2 to 1, E from 1 to 0, R from 1 to 0, T from 1 to 0, S from 1 to 0. And what we can notice is that after processing those two strings, if they are anagrams, all the values in the map are zeros. So we could just go and check whether all the values in our map are zeros. And if all are zeros, that means the strings are anagrams. If we had, for example, some extra letter here, let's say we had another S, when we were processing the string T, we would have to decrement another time. So we would end up with decrementing from 0 to -1. We can immediately check whether after the decrementation, the value of the counter goes below 0. If it goes below 0, then we can immediately return false, because that means that this specific letter appeared more times in string T than in string S. Similarly, if we had completely different letter, let's say instead of S, we had a letter X here, the way it would work that when we are processing X, we would add X to the map with the initial value 0, and then we would decrement that value, so we would end up having a -1 for X. And again, since the value is negative, is -1, we would immediately stop the algorithm and return false, because that means that X appears in the string T more times than it appears in the string S. And that's the main principle behind the frequency counting algorithm. And the time complexity for this solution is O of n, because we have to just read those two strings twice. Specifically O of 2n, because we already know that they are both the same length. We checked before we even started. This simplifies to O of n. And the space complexity is just O of 1, because in the case when string is an ASCII character string that can be at maximum 256 characters, which is a constant value. In our specific case, we were told that we only are dealing with the lowercase English letters, so the number of letters is only 26, and this is also constant. That's why the space complexity for this solution is of 1. And that's the idea of frequency counting using a map. The solution that uses map is efficient, but we can improve it slightly by using an array. And we can improve it because we were told that there are only 26 characters in the input strings. Both of them only contain lowercase English letters. So for that, we could create an array of 26 entries. And indexes would be 0, 1, 2, and 24, 25. And we would initialize all the values with zeros. And now when we are processing a character, we could use the feature of C++ that allows us to do an arithmetic operations on the characters. And it would go like this, that if our current character is, let's say, letter A, we would subtract letter A from it, and the result would be 0. That means that we can use the array position at index 0 to count the occurrences of letter A. And for letter B, we would again subtract A and get 1. So the number of occurrences of letter B would be counted at index 1 in that array. And so on. For letter Z, we would subtract A and get 25. So the last index in the array would be for counting how many occurrences of letter Z are in the strings. And if you think about it, this array is a special map which maps integer, which is our index, so index, to a value, which is also int. So previously we were mapping from char to int. Now we are mapping from int to int. And everything else is the same. So we would do the same step, process each character, and there will be one additional step that for each character we would subtract A to find a position in our array or in our map, array treated as a map, and then operate on this position, either adding or subtracting the counts. And this doesn't change any of the complexities. It basically improves a constant in our space complexity. It becomes specifically of 26, which is of 1. So in practice, this would be a slightly faster solution because it's easier to allocate array. It can be allocated on the stack locally, and the map uses a heap. But from the complexity point of view, this is a small optimization, not like critical optimization. And that's how we can use array instead of the map to solve this problem. Now let's talk about the additional question, which sort of leads to a deep rabbit hole. And the question was, what if S and T were Unicode characters? So let's assume that our strings are UTF-8 encoded. So we have encoding UTF-8. And let's say they just have one letter. So each of them has one letter. So S will equal this string of bytes, and T, or characters, and T will equal the below string of bytes. Notice that in the UTF-8, or in general in Unicode, the number of characters is way larger than the 256 values that we are given by a char type. So the way they go around this is to encode characters on more than 1 byte. So some characters are encoded on 1 byte and another ones are using more than 1 byte. And that example I have on the screen are 2 different Chinese letters. And if you notice, they have the same leading by default and the same bytes, 85 and 90. These are hexadecimal values. But the 85, 90 and 90, 85 bytes are in different order in those 2 letters. So these are 2 real valid UTF-8 characters. And the only difference is that the bytes 85 and 90 with the values 85 and 90 are the order of those bytes is switched and they encode 2 different letters. So if we were to check for anagrams using any of our methods, for example, if we use our brute force, we would sort them, we would end up with the same strings, and we would say that this is an anagram, but this cannot be an anagram because this is a different letter. So this method will not work. Also, any of our frequency methods would fail because they would count all the characters in the strings. In this specific case, they all have frequency 1. And we would say that they are equal, so we have anagrams, but we don't. These are 2 different Chinese letters. So none of our previous methods, which were tailored for ASCII string, would work in this example. And as I have said, this question leads to either more deeper rabbit hole, and this is for the reason of Unicode equivalence, which means that certain character in Unicode can be encoded in more than one way. For example, there is a letter E with the accent, which can be encoded as Unicode 0.00E9, but it can also be encoded as 2 characters. So there is a E and there is an apostrophe or accent after the E, and this is encoded using 2 code points, U0065 and U0301. When we process the Unicode strings which contain that specific letter, but the letter is encoded differently in, let's say, string S, and is encoded differently in string T, we would not be able to do it by just looking at the values in the string. We would need to have a layer of implementation that is able to understand those encodings. And the simple way would be to process, not simple, but the simplest way would be to process both strings and normalize them to one encoding. So for example, to make sure that letter E, if it is present in the second string, these 2 are replaced with this one encoding. So we would end up with 2 strings having the same encoding, the same way of encoding for any letter. And only after that we could build a map, and the map would have to have like a Unicode character here or string, and that encodes a sequence of those encoding and the frequency. So int and let's say string or some type of Unicode character. And only after that we would be able to go back to our idea of frequency counting. So we could count the frequencies in one string, count the frequencies with second string, and then compare if they are the same. So this is much more involved, and it's impractical to implement in the interview settings. But in general, that would be the idea to explain what would happen if those strings were Unicode strings. Let's write code for our solutions, starting from the brute force solution. So the first thing we have to do is to compare whether the lengths of the strings are the same. So if the strings are of different sizes, we will immediately return false because they cannot be anagrams. The next step is to sort both strings. So we have sorted both strings, and the last part is to check whether they are equal or not equal. In this case, we can simply return the value of the comparison if the S is equal to T, which if they are, will return true, and that means our strings are anagrams. If the comparison is false, that means the strings are not anagrams. And that's the entire solution. Let's build it. It builds okay, and let's run the test. And all the tests have passed. Let's write the code for our second solution, which will be using unordered map to do the counting. So we start again from just comparing the sizes of the strings and returning false if they are different. And if they are different, we return false because they cannot possibly be anagrams. So let's now define our map. In that map, we will be counting how many times a character, which is a key in the map, appears in a string. So let's now process the first string. So for string S, each time we encounter a character, we just increment a count in our map for this character. And now we are ready to process the second string, string T, but this time we will be decrementing the counter. And after we decrement the counter, we have to check whether the value for this counter is negative. And if it is, that means we can return false because we have more characters in string T, more specific instances of this character or occurrences of this character in string T than in string S. Otherwise, if we reach beyond that second for loop, that means we never encounter a character that after decrementing would cause the map count to go beyond 0. So we just have to return true. And that's the algorithm. Let's build it. And let's run the tests. And all tests are passing. So this was the algorithm that uses map. Let's write the optimized algorithm that uses array to count the occurrences of the characters. And as usual, we start from comparing the sizes, making sure that size of T is equal size of S. If it's not, then we will return false immediately. Now we are ready to define an array for our frequency counting, and the array size will be 26 because we are promised that the strings will only have a lowercase English characters. So we defined an array of size 26. The elements of the array are ints, and we are initializing it by those using the universal initialization. So the initial starting values in that array are all zeros. So let's now process the string S and count the occurrences of characters in string S. So we use the range for loop, and the only difference between the solution and the solution that uses map is that we have to subtract a character A from our current character C in order for the value, the index of the array counts, to be between 0 and 26. So let's now process the string T, but this time we'll be decrementing the values inside our array for the specific characters. So we decrement the counter for a character C, which we track inside our array. And if this counter goes below 0, that means we can return false because the number of occurrences of character C is greater in string T than it was in string S. So we return false if the value inside our array for this specific character C goes below 0. Otherwise, if we were able to process both strings successfully, we just return true. And that's the algorithm that uses an array instead of a map. Let's build it. And let's see if the tests are passing. All tests are passing. So we have coded the algorithm that uses frequency counting and uses an array instead of a map. Let's make sure our solutions are passing LeetCode tests. We will start from the brute force. Let's see if it runs. It runs. Let's try to submit. The submission succeeded. So let's try another one, the one with the unordered map. Let's see if it works. It works. Let's submit this one. We were able to submit. So let's try our last solution that uses array works. So the solution works. Let's see if we can submit to LeetCode with no problems. And we were able to submit and pass all the tests. So our solutions work. This is the end of the solution. The source code is available in the GitHub repo shown on the screen.